basically smart design. All right. So in a second now, you'll see my screen. Okay. All right. So can you hear me?
Loud and clear, sir.
All right. So hello. Sorry, I'm having a really terrible network.
Okay, so sorry about that.
Sorry, I'm okay. All right. Let me see. Let me know when you can see my screen, please. Can you see my screen?
Yeah, I can see your screen. I think
Okay.
the slide is a bit small in size. Probably put it in presentation mode.
Okay. All right. Can you see it clearly? Can you see it clearly?
Yes, sir. I can see the slide clearly.
Okay.
But
All
I
right.
don't know.
So
Can we zoom the screen, like present the slide so we can just see only the slide, because we are seeing all the whole PowerPoint.
okay, give me a sec.
Okay.
Okay. Let me just do it. All right. So before all that, let me just okay. So as I was saying, optimization. Okay. Optimization not in the sense of like optimization, but kind of like in the sense of making a smart design, right? I remember last what we were talking yesterday, I made mention of the reasons why meshing, and because and I remember Tabos was asking a question about how different, if you wanted to like optimize your designs and what you would actually need to do to actually get this done. You understand? Now, optimization in the sense I mean is like smart design. Okay, like what do you do? No, what do you do to have an actually smart design, a design that does what it's supposed to do? Okay, like this is me trying to kind of like relate what real life simulation is and what actual like simulation is in when it comes to like in the theoretical aspect of it all. Now, for optimization, you need three things, right? First thing you need is the variable. Like I said, your geometry plays a big plays a big role in the entire simulation result, of course. Now, when I say variable, I mean like your dimensions or your parameters, okay? Things you're allowed to change. Like when we started yesterday, and I said things like your fillets, things like your chamfers, you understand? So these are variables you can alter to get like whatever result you're planning on getting. Okay. Now, the second ingredient I would say for optimization would be constraints. Okay, constraints as in like these are what you can do and what you can't do, right? These are sort of like limits your design, your whole simulation should not exceed. Let's say working from the back, we say a you cannot have a force that is much more than, you cannot have a stress value that is more than this. You understand? Something like that. And why this is important is because maybe, for instance, you have a like, because they both work hand in hand. Okay. Okay. Let me share my screen now. Just let me know when you can see the screen. Okay. Yeah. So as I was saying, it's so why is it so slow? All right. Can you see my screen properly? So
Yes,
can you see my screen
sir.
properly?
Yes,
Okay.
sir.
All right. So now, like so, first ingredient I said is first ingredient is your variables. Second ingredient is your constraints, and then let me know you can still see my screen, right?
Yes, sir. Breaking points. That's what's
Okay.
showing.
Okay, right. Then your third what's it called ingredient is your goal. Okay, so what are you trying to achieve? What's the whole idea? Okay, now brings to breaking point. Breaking point now, simulating a 4 level dose of impact for steel. Basically, what we're trying to do here is kind of like trying to see um how much um how much relatability we can get from simulation in itself.
My effort is sorry to interject, Mr. Joseph. I cannot see your screen.
Okay. Um, Timothy, please, can you see my screen?
Yeah, I can see your screen on my end. I don't know, probably it's your network or you try it again. Okay.
Okay. Can you see my screen now?
Yes, yes, yes.
Yes, sir.
Okay. All right. Okay. Now, I'm just going to give a brief rundown. Okay. So the whole idea about this simulation is trying to see how this specific steel door is going to react to like different scenarios. Okay. We are going to up the scenario and see what happens. Try to like show you how it would react in real life. Okay. Now, like I said yesterday, what are the first things you do when you start in simulation? If you remember, I said geometry, I said material, then fixtures, geometry, material, fixtures, your force, your mesh, and then your result. Okay. Now, material, we're using mild steel, right? The ASTM A36, the only value of importance right there is the 36 at the end, which tells you its strength grade. And then the ASTM at the front of it, it tells you under which standards of material, which kind of like are you working with this certain international standard, are you working with certification standard? Now, threshold when it comes of the steel itself you're using is 250, all right? With an ultimate tensile stress of 400. We've saw that whenever you're selecting materials in SolidWorks, you get the ability to choose any material based on its density as well as its yield strength, okay? Because like we said, stress is the yield stress, is the yield strength of your material, all right? Now, for the door itself, the door is a 2000 by 900 millimeter security door. It has an it has a thickness. Okay, I think a thickness of 10, if I remember, because we're trying to mimic an actual door. All right. So we first things first, assumptions we are assuming for this simulation. Sorry, the assumptions we are assuming for this simulation is that the door is actually fixed. Okay. So what we will be testing, we'll be testing four scenarios. First scenario, we'll be testing human punch, which is about 800 Newton. So then next we'll be testing a professional human boxer, which is about 3000 Newton. And then we'll be testing a battering ram, which is 12,000. This is because this can be handled by multiple, like people, more than one person can, like the ones police officers use. And then we'll be testing for a car. All right. Now, okay, the door thickness is 3 millimeters. All right, because we are trying to kind of like mimic real life. Now, what you should understand is now we've done okay, we've selected the material for this, and then we've picked the geometry, we've picked the size. Now, when it comes to geometry, one thing we didn't talk about is the space, like where the force is going to be impacted. Of course, if you punch a door, you cannot punch a door like the impact cannot be on the entire space of the door. All right. So what we do is we pick a specific point in that door itself. All right. Pick a specific point for that door, and then how it's picked is you can use cut, but cut is going to create a hole between like a space, a gap between that section. So you use your split line to remove it. All right. Now for first scenario, let's say you've from what we did yesterday, you've applied your material. Now you've selected your fixtures. They're going to be fixed at the edge where hinges are supposed to be. Makes sense, right? And then next you try and put your forces. So 800 Newton easy, but it has to be where the point is. A human hand is roughly 80 millimeters if a punch of a person, like the diameter for your arm itself. So using that, we can easily mesh. And then when you look from this mesh, you can see you can see that the meshing converges at certain points. All right. This was done using what's it called? Using mesh control on spaces where you want, like on spaces where you know that the particles or the what's it called? There are certain types, like there's fillet in it, or there's a chamfer there, or the features that are so tiny. Although for the entirety of this design, those parts are not really relevant. The reason why I didn't really ignore it is because when we continue moving to the, like the as we continue moving, you start seeing that those areas become sort of like an area of impact. So it's better to deal with the meshing there at first than kind of like going from the beginning. Now, when you run your result for the first door, simple enough. The simulation, the stress we get was about 34.6 megapascals. Okay, so easy stuff. Is not the displacement was very negligible, right? And then you have a factor of safety of 7.2. So it tells you you would need 7 times that punch to actually make that impact. So with that, obviously, a human arm cannot do that. All right. Then scenario two, a martial artist. So this, we're talking about somebody that's trained. Okay, someone that knows what he's doing, someone that knows how to throw punches and how to position their body. They're no longer punching like babies. It's kind of like putting their full body into it. You understand, right? So now putting it into perspective, like I said, here, it's kind of like taking a full-grown grizzly bear and kind of like, you understand. So, and now because of the concentration of that part itself, there's a concentration there. We're still using the same what's it called? Now, the first, if you're trying this yourself, I would recommend you kind of like tweaking it a bit. You don't need to use 3,000. It's a range 3,000 to 5,000. So whatever one you kind of feel like using, you use it, and then you run your simulation. Now, mind you, when you're running simulations for this, sometimes you don't really have to do much. You've done most of them. So what you're actually only changing is the force itself, but you still have to remesh, right? You still have to kind of, when you change a certain value, SolidWorks prompts you to remesh. You remesh and you run your simulation, and you see that we saw that the real stress was about 118.7 megapascal. It's still below the 250 threshold, and then the material is still safe. Now, of course, when you check your deformation, there'll be a little bit of dent, but it's going to be plastic. Sorry, it's going to be elastic, because of course it's going to kind of like deform, and then since the yield strength wasn't really exceeded, it's going to deform, and then it's going to come back to its original position. Okay, but then again, if you smash your arm with that amount of force, the arm goes, the dust still remains. All right, good. Scenario three, we are now using a battering ram for it. Okay, so we are kind of like using human, let's say 2 to 3 people using a slamming on the door. And then, of course, what I did was, now we noticed that well, the diameters for this ram is not going to be the same thing as 80 for human arm, right? So taking that into account, I said, okay, we can increase it, and then we increased it to 125 millimeters, okay, prior to the like 80 for human arm. So you make your research, you know what it actually should look like, right? And then you run your simulation. Quick run gives you a result. Now, mind you, these results we are getting are not 100% entirely correct. All right. Why I say this is because when you want to do something like this, there is a lot of factor to give a precise answer. But what we are trying to get is an overall answer and see how a certain material, not like a fun way to see how a certain material would actually relate when it comes to like design, when it comes to simulation as a whole. Yeah, please, Timothy, can you hear me?
Yes, Donald.
All right, thank you. So now, all right. So now, what result did we get? The yield strength for this material is 250. 3 to 4 people use a battering ram for the door. Obviously, it's gonna go right. But what SolidWorks doesn't show you is actual deformation. SolidWorks won't show you where the door smashed open, right? It tells you, look at your result, and you know that, whoa, your threshold is 250 and you're getting a stress of 632. So you should know that the material is actually smashed. Why SolidWorks won't show you is because of you cannot smash to infinity, like it cannot deform to it's just gonna keep deforming. If you want to really see it clearly, all you have to do is go to your deformation scale and kind of like instead of true scale 1, just increase it to like 60. You want to see it 60 times normal. Understand? So you get this kind of like view of the full like kind of like deformation itself. Okay. So now what we've done so far is we're seeing how much different scenario, how different forces are change, how they change, and how our results vary and vary and vary. Now this is very important because when you get a punch, when you throw a punch of like 800 newtons, your mind tells you, okay, well, you kind of like doubt, like, okay, seriously, how would we know? I mean, I guess if we increase the point, you understand? So you increase it and you see, okay, wow, there's a huge difference, and then you increase it and then you see there's a huge difference, and then you increase until you get to the battery RAM. All right, and then finally a low speed vehicle. Now a low speed vehicle is not going to slam on a 125 diameter circle. It's going to like slam the whole thing, like extend throughout. Okay, so we're taking that into account, but it's still not precise because we're not taking into account, we're assuming that the car itself is a flat front. So there are things like bumper, the things at the front of your car that actually makes it kind of like, you know, get that shape itself. Okay, but we are working with an assumption that if we are now more focused on the force of this car now, so we're saying forces that range from between like 60,000 newton and above. Okay, and it's not even hard traveling on high speed, kind of like low speed. All right, so you run your mesh, you do the same thing, and then you get your result. Now, even at default deformation, you can see how much it changes. All right, you can see how much deformation comes out from it. It is steel that actually works, that's actually 250 megapascal. Now against a stress of 120 or 154, 1540. So you see something like, you see a different huge change right there. Okay, so you can see it deforming, and then when you look at the deformation with 60 millimeters, you can know, okay, it actually you understand. Good. Now there is one thing I noticed was when I started my first design. Okay, if you go back to the first slide, when I started the design, okay, good. Now look at this particular design. You notice that there is a Z, there's some sort of Z at the back of the door. Okay, when I first ran the simulation, when I started the whole thing, right, I kind of like thought, okay, this is what's going to happen. You run your stretch, you put your door, and then bam, a human punch was able to kind of like break the door, smash to the door, human punch. So I thought to myself, why did this happen? You understand? This doesn't make any sense. It's a door. Human punch shouldn't actually do much. And then I started making research and I figured, okay, it's a steel door. And then with the millimeter it has, so obviously, so what we would need for a steel doors are not really plain. They have this sort of like reinforcement on the back. And I was a bit skeptical about the reinforcement parts because I thought, come on, it wouldn't make any much difference. I mean, this is not real life. You understand? Like, it's not real life. Like, it's not something you would just say you don't added a reinforcement and then it just worked. You understand? So I said, okay, what the hell? I tried it. And then I noticed it's actually worked. I got a use strength of 34. I was so like, because it was kind of like, now I know if I slam in some sort of reinforcement, I'm sure the door would be so strong enough to withstand um let's say the battery RAM. You understand? Now you have the resource and the software to do it, right? And your client tells you, I want this, I want a door that can withstand the police battery RAM, and you give it a door. So you don't just do the door and hope and pray. You can now test your door and see, okay, this is what happens, right? When we put this door under different condition, right? You say, okay, when we tried human punch for this specific door, it was safe. Okay, so nobody's gonna come and punch your door for us. Okay, but what if it's a professional person? I would say, okay, if it's a professional person, well, it would still stay. But if it's a military battering system, you understand? Now, if you were asked rather, okay, I need you to optimize this door so that the battery RAM doesn't tear through it. Okay, then you start thinking, first things first, you start thinking, you now, like I said, you now have variables, constraints, and goal. You get your goal. What's the threshold you are trying to meet? Okay, sorry, constraints. Where's your threshold you are trying to meet? We're trying to keep it below 250. Okay, you've gotten your goal. What variables can we change? Can we add more fillets? Can we add more reinforcement? You understand? Okay, you get that right. And then the goal, what are we trying to achieve? We want to make it stronger. All right. Now, you now have a lot of things to think about. You can start thinking about, okay, to make this better. From our simulation yesterday, our test was about our test material alloy steel was about 420, I think. 420 or 640. 640, I think. 640. So 640, right?
620.
Okay, good. Now, if you swap that for this design, for this particular one, and you swap it for this particular one, and then you run your simulation, okay, you now start getting a whole different lot of problem. Okay, you say it works, right? It works. It stays, there might be a bit of deformation, but it actually holds. But what you start thinking about, if the person kind of like at this point, if a person punches it, it's gonna fall, right? So that now brings your mind towards factor of safety. How many times should this actually fail? You understand? So you start thinking, okay, materials alone won't actually do the fix. Maybe we should add more reinforcement, or we should increase the thickness. You understand? Or we should reduce the client's own expectation, right? What the client actually need. Okay. Now, I don't know. I don't know any door that would withstand a vehicle, right, slamming into it. Yeah. So, but you could actually optimize for it. So, of course, you will see the changes. You start thinking about when you start thinking about material. Okay, material changes are not that visible. I mean, you just know that the cost for this specific material that is probably a much more stronger is going to be higher. And then when you start going towards the next one, like adding thickness, okay, you add the first thickness, let's say add 10 millimeters, and you notice, okay, it's still below the threshold. And even at that, you start thinking, okay, nestiness would be factor of safety. Okay, nestiness would be where exactly is this failing from? So you don't go randomly putting so you don't go randomly optimizing everywhere, kind of like adding stuff you don't need, right? You start thinking about cost, you start thinking about where specifically we are having this maximum stress from using your probe, and then we can now say, okay, this is where it actually comes from. Okay, now in conclusion, I would say one, mass always wins. Okay, the ribs themselves could actually do the ribs themselves can actually stop human, you understand, right? You can actually stop human punch, and then but as the force increases, as you start putting through different scenarios, you start getting what's it called? You start getting multiple like scenarios. Okay, still things start coming to mind. Okay, what if? So at the end of the day, the higher the force applied on it, the material is going to fail. So it's your duty to work around it. Okay. Then next, the puncture threshold. Material failure occurs at approximately 12,000. So up until even when what's it called? Even when now, simple question. If I asked you, if I gave you a stress, right? I gave you the stress itself, and I asked you, this is what you should do. Take a specific stress and kind of like look for a way to kind of like reverse engineer the whole thing. You know, this is the particular stress you want. Like I said, if you're trying to solve a problem, there would be multiple things to actually solve, like multiple variables and values to take into account. Okay, but easily you get one variable and then you start working. You get your specific threshold. You say this is the stress that the client wants. With that, you can start working backwards. What material to use, what kind of hinge to use, the thickness of the door, the size of the door, the height of the door. These things start mattering. Okay, then design optimization. Like I said, the rib itself, the Z 10 I put, the Z reinforcement I added played a big role, much more than I expected. All right. So I thought about it. and I figured, okay, this is something that would work, right? And then let's not talk about the fact that if I wanted to increase the threshold more, I could easily increase the thickness or the size of the rib itself. Okay, and then we start getting much more strength. Okay, so the whole point of this is now, when it comes to optimization is supposed to sound like you kind of like removing from your design, but it can also be you adding to that same specific design, right? This is you trying to show that, okay, you get what's it called, you're not just trying to do for just for the sake of it, you're doing it with a purpose. And what's the purpose? The purpose is whatever the client wants it to be. The client wants the door to be stronger, or the client wants the door to be cheaper. Okay, the client wants the door to be safer, or the client wants the door to be aesthetically pleasing. And then when you start thinking aesthetically pleasing, you start thinking, well, a Z slab right there wouldn't do it. Okay, so you start thinking about the different ways to work around it. Okay, so thank you for following through to the end. You can reach out to me. You can ask any question if you have any of them. I'm open to answering. Okay, Timothy. Hello.
Yes, sir. We can hear you, sir.
So all right, this is the end of the presentation. I think, yeah. Okay. Yes. So any question you have, anybody has any question, I can answer now. Then okay, yes. Also, Timothy, can you hear me?
Yes, sir. I can hear you.
All right, thank you. So we what I have kind of like this presentation I just did right now. I think I should send you the what's it called, the file itself. So in case anybody wants to practice it, right?
Okay, okay. That would
All
be
right.
wonderful.
All right, amazing. What I'll do is I'm going to include I'm going to include a video recording of the entire thing, the entire process. Okay, kind of like why I did what I did. You understand, much more in depth than what we just did here. So I'm going to send it to Timothy today or tomorrow, and then you can share the link with you guys, and anybody that wants to watch it can easily watch it and make the simulation yourself. And then if you come across any problem, if you even want to add more scenarios, I would really appreciate it. If you want to add a person slamming through the wall, anything you want to add, just you can add it there. Okay.
Thank you very much, Mr. Joseph Celestine. I think we don't have much questions here. So I will be dropping the link for today's attendance. So just bear with me few seconds. I'll drop. Okay, I think there's no question at the moment. So just bear with me while I send the link to the today's attendance. Mr. Joseph, are you still on the call?
Yes.
So thank you very much. Really appreciate you joining the call today and sharing with us. It was such a wonderful session. If you were here yesterday, you would really appreciate today's session, because a whole lot of things were talked about, and different case. Yesterday's session we only did one case scenario, and today's session we did there are multiple scenarios. With the experience of yesterday's session, you can apply it to today's session, and then you'll be able to create your own simulations of those use case. So I would appreciate if you go back and still try it. Video tutorials will be dropped for you to go back and watch them and practice them on your own. And like always, if you have any question, the group chat is there for you to ask your questions, and we are always ready to answer your questions. And also, you can also come to tomorrow's class and then ask any of the questions that you have. Thank you very much. Thank you once again, everyone, for joining today's call. I will be dropping the link to the attendance now. Please make sure you fill the link before leaving the call.
All right, thank you, everyone. Good night, guys.
Good night, sir. So here is the link. I just dropped the link now. So I just dropped the link to today's attendance. Please do well to fill the form, as you filling this form and validates that you attended today's session, and then that's what we use to collate your certificate of participation. So thank you very much. In the next few minutes, I'll be ending the call. So do well to fill the attendance. So thank you, everyone. Thank you, guys. I'm ending the call now. Thank you very much for attending today's session. We meet the same time, 8 p.m. tomorrow for the last day of our bootcamp. Thank you very much for attending.